High in the mountains of northern Chile, a telescope the size of a small building spends its nights doing something almost boring to describe. It points at a patch of sky. It takes a picture. It waits. Then it points at the same patch again and takes another picture. Over and over all night, every clear night. Nothing about that sounds like a discovery machine. But buried inside those repeated pictures, astronomers just found something that had been sitting in our own solar system the entire time, unseen. Over 11,000 asteroids that no human being had ever recorded. Hundreds of them lie far beyond Neptune, out in the cold, slow-moving edge of our solar system where almost nothing has been mapped. 33 of them pass close enough to Earth's orbit to matter for planetary defense. And this wasn't even the telescope's real survey. This was the warm-up. The telescope is called the Vera C. Rubin Observatory. And what it just handed astronomers is being described as only the beginning of something much larger. A possible reshuffling of how many objects we think actually make up our solar system, and a fresh set of clues in the decades-old hunt for a planet we have never confirmed but have long suspected might be out there. So how did a single observatory, running early tests, outdiscover generations of asteroid hunters in a matter of weeks? And what happens when this telescope stops warming up and starts running for real? The Vera C. Rubin Observatory sits on Cerro Pachon, a mountain peak in Chile chosen for its dark skies and dry, stable air. It's a joint project of the U.S. National Science Foundation and the Department of Energy, named after the astronomer Vera Rubin, whose work on galaxy rotation in the 20th century produced some of the strongest early evidence that dark matter exists. Her name is now attached to a telescope built to do something almost as ambitious: photograph the entire visible sky over and over for 10 straight years. At the heart of the observatory is the LSST camera, mounted on an 8.4-meter telescope. The camera itself is roughly the size of a small car and carries a sensor with 3,200 megapixels, about the same number of pixels as 260 ordinary phone cameras combined, all pointed at the sky at once. It is, by a wide margin, the largest digital camera ever built for astronomy. That scale is the whole point. A telescope this size, with a sensor this large, can photograph an enormous slice of sky in a single shot, then come back to that same slice again and again through the night. The asteroid discoveries didn't come from the observatory's headline decade-long survey. That survey only officially began this summer. They came from something smaller, an early testing phase using the Simone survey telescope and the LSST camera together, meant to shake out the instruments and software before the real work begins. Even so, in about a month and a half, the telescope produced roughly 1 million individual observations. Astronomers sorted through that flood of data and identified over 11,000 new asteroids, plus more than 80,000 already known ones, some of which had actually been lost, meaning their orbits had become too uncertain over time to predict where they'd be next. Rubin found them again. The results were submitted to the International Astronomical Union's Minor Planets Center, the official global clearinghouse that verifies and catalogs solar system objects, and the center confirmed them. To understand why that number is so startling, it helps to understand how asteroid hunting has traditionally worked. For most of the history of astronomy, finding an asteroid meant finding a single point of light that didn't belong. A star stays put, night after night. An asteroid drifts just slightly against the fixed background of stars. Spotting that drift required photographing the same region of sky more than once, then comparing the images by eye, or, more recently, by computer, looking for the one dot that moved. Once you found a moving dot, you had to track it again on a second night, and a third, before you could even begin calculating an orbit. Miss a night, lose the object, and you might not find it again for years. That's the process that has generated most of the roughly 1.5 million asteroids known before Rubin ever turned on. It took over 2 centuries. Rubin doesn't hunt one dot at a time. Its camera captures enormous swaths of sky in a single exposure, then returns to the same patch repeatedly through the night and across nights, building a dense timeline of images. Software developed specifically for this kind of data, built by researchers Ari Heinze and graduate student Jacob Kurlander at the University of Washington, sifts through the resulting flood of pixels looking for anything that shifts position in a way consistent with an orbiting body. Instead of a person squinting at one dot, it's an algorithm checking millions of potential dots at once, then stitching the faint, repeated movements of each one into a coherent path across the sky. Heinze has described Rubin's unusual observing pattern as demanding an entirely new kind of software architecture just to keep up with the data. And once that software was built, it worked on the very first large batch of real data it was given. What used to take a research team years to confirm for a single object, the software can now flag in a matter of days across thousands of objects simultaneously. That shift in method is why the numbers from this test run look less like ordinary scientific progress and more like a jump in scale. Mario Jurich, the University of Washington astronomer who leads Rubin's solar system science team, has described this first large batch of discoveries as only the tip of the iceberg and said plainly that what used to take years or decades to find, Rubin can now uncover in months. Among the 11,000 new asteroids, roughly 380 are trans-Neptunian objects, icy bodies orbiting out past Neptune in the dim, mostly unmapped region of the solar system, sometimes called the Kuiper Belt and beyond. These are some of the least understood objects we have. They move slowly, they're faint, and because sunlight out there is so weak, it can take a human lifetime to complete a single orbit. Every new one adds a data point to a map that has, until now, been built one faint discovery at a time. Closer to home, 33 of the new objects are near-Earth asteroids, bodies whose orbits bring them within about 1 1/3 times the Earth-Sun distance. These are the objects planetary defense researchers care about most because their paths can, in principle, intersect ours. None of the newly found ones pose any known threat. The largest is roughly 500 meters across, big enough to be worth tracking carefully, but with an orbit that keeps it safely away from Earth, as far as current calculations show. Still, every additional near-Earth object cataloged is one fewer unknown in the sky, and Rubin found 33 of them essentially as a byproduct of a software test. Planetary defense depends entirely on this kind of cataloging. An asteroid can't be assessed as dangerous or harmless until it's found and its orbit is calculated with confidence, and the objects that worry astronomers most aren't the ones already being tracked. They're the ones still missing from the catalog altogether. A telescope that can add tens of thousands of well-measured orbits in a matter of weeks doesn't just make the sky more interesting. It makes the sky more known, which is the entire foundation planetary defense is built on. It's worth pausing on how young this discovery run actually is, because the timeline makes the scale even stranger. Rubin's asteroid hunting capability didn't arrive fully formed. In late 2024, during initial testing with the observatory's smaller commissioning camera, the system found just 73 asteroids, a modest proof of concept. In the spring of 2025, during a phase astronomers called First Look, that number jumped to 1,514. Then, over roughly 6 weeks last summer, using still unfinished engineering-grade data from the full-scale telescope, the count exploded to more than 11,000. Each step wasn't just a bigger haul of asteroids, it was a demonstration that the underlying system itself was scaling, getting faster and more capable with each test. And the actual 10-year survey, the one this telescope was built for, hasn't even begun. That's the part that turns this from an impressive test result into something closer to a preview of an entirely new era in solar system science. Once the full survey, formerly called the Legacy Survey of Space and Time, gets underway, researchers expect the discovery rate to climb even further. Rubin scientists have said that during the survey's early phase, the observatory is expected to find roughly 11,000 new asteroids every 2 to 3 nights, not per month, not per year, every few nights. Simulations run ahead of the survey suggest that over its full 10-year run, Rubin could ultimately reveal millions of previously undetected asteroids, more than doubling, and potentially far exceeding, everything humanity has cataloged to date. So what does a solar system that suddenly has millions more known objects actually tell us? Part of the answer is about history. The distant trans-Neptunian objects Rubin is starting to map aren't just isolated rocks and ice balls. Their orbits carry fingerprints of how the solar system's giant planets moved billions of years ago. Early in the solar system's life, Jupiter, Saturn, Uranus, and Neptune are thought to have migrated substantially from where they first formed, and that migration would have scattered smaller bodies into the strange, tilted, elongated orbits many distant objects occupy today. Each newly discovered trans-Neptunian object is, in effect, another data point in reconstructing that ancient rearrangement, a fossil record written in orbital mechanics instead of rock layers. The other part of the answer is more speculative, and astronomers are careful about how they frame it. The possibility of an undiscovered 9th major planet. For years, some researchers have pointed to unusual clustering in the orbits of a handful of distant trans-Neptunian objects as indirect evidence that a large unseen planet's gravity might be shaping their paths from far beyond Pluto. It remains an open hypothesis, not a confirmed discovery. No one has directly observed such a planet, and other explanations for the clustering haven't been ruled out. But researchers working with Rubin's data, including Kevin Napier at the Center for Astrophysics, have pointed out that a much larger, more complete catalog of distant solar system objects is exactly the kind of dataset that could eventually settle the question, either by strengthening the case for a hidden planet or by explaining away the clustering entirely. Objects like the ones Rubin is now finding offer what Napier has called a probe of the solar system's outermost reaches, relevant both to that planetary history and to whether a 9th planet is truly out there. There's also a fitting symmetry buried in who this observatory is named for. Vera Rubin spent her career studying how galaxies rotate and found that stars at their outer edges were moving far too fast to be held in place by the visible matter alone, evidence that something unseen, now called dark matter, was shaping the galaxy from the shadows. The telescope built in her name is, in its own smaller way, doing something similar much closer to home, revealing a solar system whose full population was always larger than what we could actually see, simply because no one had ever looked at it fast enough or wide enough to notice. It's important to be precise about what has and hasn't been established here. What's confirmed, the observation data, the orbital calculations, and the object counts have been submitted to and verified by the Minor Planet Center, the internationally recognized authority for this kind of confirmation. What's still open? Some newly detected objects, especially the faintest and most distant ones, will need additional observations over months or years before their orbits are pinned down precisely. That's simply how orbital astronomy works, regardless of which telescope does the finding. And the question of a ninth planet remains, as it has for years, an intriguing possibility supported by circumstantial evidence rather than a settled fact. Rubin's data may eventually help answer it. It hasn't answered it yet. What has changed, unmistakably, is the pace at which we're capable of asking the question. For most of astronomical history, mapping the solar system's smaller residents was a slow, patient accumulation. One asteroid, one orbit, one confirmation at a time, spread across generations of astronomers. In a month and a half of preliminary testing, a single telescope matched a meaningful fraction of that accumulated total, then went on to demonstrate it could keep doing that every few nights once it's fully operational. That's the real story behind the number 11,000. It isn't just a count of new rocks in the sky. It's a demonstration that the tools for understanding our own solar system just underwent a step change, and that the map we've been building for 200 years was far less complete than we assumed. Somewhere in that flood of new data may be the clue that finally settles whether there's a ninth planet waiting in the dark. For now, the telescope keeps doing the same quiet thing, night after night, pointing, watching, waiting for something to move. If you had to guess, what do you think Rubin finds next out past Neptune? Another world, or just more empty, icy dark?